nothing in there wanting to compare their pre to their post.
Well, I thought in their pre they had a motivational interview.
They did, but it wasn't being compared. It was just using as a predictor. So the key was right from the beginning, we're trying to predict how well they did in their post test. So we're using all those factors to predict one thing at the post test. So it was a multiple regression thing. Bunch of VDVs, they could be divided into no IVs because there's no, in order for time to be an IV, you have to be comparing time 1 to time 2.
I thought that they were.
Yeah, I mean, it sort of sounds like it, but actually the way it's stated, it was all about predicting how they did.
So anytime you hear pre-post, it's not necessarily comparing. You just
It has to be, it could be, but you have to be deciding whether they're trying to use it as a predictor or as a comparison.
Okay.
So they could have done that. They could have said, well, we want to see how, I mean, they also did some other things, but wouldn't make much sense in this study, would it? How would their pre-post comparison tell you how well their initial skills predicted their later skills? The prediction is the key there. So it turned out that the initial skills, rather than any of the socioeconomic stuff, predicted how well they actually did after the training. So
doing the pre and the post, you got to have a pre-score so you know how much they improved. And you can take the improvement and see how much.
You could do that, but you could just also use pre as a predictor or post too. That kind of controls for how well they started in the beginning. But I sort of said that the post was a different kind of score anyway, to make it easier. Actually, they did use both of them that way, but they didn't do any comparison, so they just used them as predictors. Okay. So today what we're going to do is start on dichotomous measures. We're trying to split up the computer usage, so Dr. Nollenberg's class is doing SEM now, we hope. I saw her running in late. So and then after the break, we'll go on the computers and do the SEM that we weren't able to do in the homework. We'll do one ourselves here in class afterwards. I'll go through the observations and parameters, that part's, whatever else you need me to review with that. Then we'll do one, it's the one that's actually in the book, because then you can actually look at it. We can come up with our own models and do an SEM. So we got a pretty good review of that after the break. We may not have enough time to finish all of the dichotomous stuff today, which we'll just finish that next time. Okay, so first thing is let's think about dichotomous measures. What we've got so far are two of them that we've dealt with. One is chi-square, sorry. And the other one is point biserial. All right, point biserial is a correlation between a dichotomous measure and a continuous measure. So remember, point biserials are calculated as Pearson correlations. The same calculations apply. But once one of the measures is dichotomous, then it becomes a point biserial. And what happens in correlations when you have a limited range of the scores? What happens to a correlation coefficient if you have a limited range of scores? Go up, down, or stay the same?
Down.
Down, right? So it's going to limit the correlation if you don't have enough variability. So point biserials, it's good to remember, are limited by their nature. They cannot actually be, you can't get a perfect one for a point biserial. With the best optimal conditions, you can get like a 0.82 correlation between a continuous measure and a dichotomous measure. So some people think there should be a measure for attenuation for that, so you can kind of justify the numbers meaning something. And there's controversy about that. But it's good to remember that, like if you see a 0.7 on point biserial, that's a really high correlation. You just can't get it much higher than that. It's also limited by the split. So if the dichotomous measure is 50-50, that's optimal. If the dichotomous measure is 80-20, 80 people in one group, 20 in the other, that really limits, I think that takes the maximum down to something like a 0.63. So the splits do actually limit you a little bit more too. So if you're in a situation where you're looking at those, you have to kind of pay attention to them. The other one we've talked about, but we haven't really gone into, is a chi-square, which is a relationship between two dichotomous or two category variables. have to be dichotomous. The most common use of that you're going to see in study after study is just looking at group equivalents before the study. So in this study, they actually did two different kinds of training, one in person, one in online or tape-based. And they wanted to compare the groups ahead of time, so they wanted to compare them on ethnicity, gender, so you just say those two. Well, those are both categories, all right, so you can't do t-tests. So you end up doing a chi-square for group equivalence. So imagine you have a situation where your study had two treatment groups, treatment 1, treatment 2, and a control group. And that you had, for your marital status, you had married, single, or divorced, just to pick those. And let's say the numbers were as follows: 51, 24, 25, 45, 20, 30, 49, 21, and 29. So the chi-square allows you to see whether between the three treatment groups the distribution of marital status was different, more different than you'd expect by chance alone. Okay. If you do them by hand, you may have had this in a previous life. What you do is you get your totals. Oops, I'd actually do this. You get your totals in both directions. You multiply the row total times the column total divided by the grand total to get an expected value for each cell. I'm not going to go through this because we never have to do this really by hand anymore. And then you get expected values for each cell. Everybody get what I mean? So this is a row total times the column total times the grand, divided by the grand total. If somebody wants to do the numbers, we can do them, but I'm not going to carry it all out. These are observed values. These are expected values, right? So then chi-square equals observed minus expected, quantity squared divided by expected. Sum of those. So for each cell, you get an observed, you get an expected, you subtract them, you square it, divided by the expected, and you add all those 6 cells up. That gives you a chi-square. You can kind of see how it works. What you're doing is getting the general trends and seeing how far each cell differs from the general trend. And the more they differ, the more that's going to add up to being a bigger chi-square. Degrees of freedom are rows minus 1 times columns minus 1. So 2 times 2 is 4 would be the degrees of freedom. And there's a chi-square distribution that is a non-normal distribution that is in the back of all the textbooks. And you can look those up and see whether for those degrees of freedom your chi-square is significant or not.
I got when you said row total times column total divided by grand total, and then what did you say you got for that?
So then this is an expected value. This is an observed value, right?
Yeah.
And that's it. This is kind of, someone do that first row for me with a calculator, would you? So we have to add those and add those. I didn't do the adding, I'm sorry. Should have done it ahead of time. You get a number for that one yet?
Nope, I'm doing the row.
Doing the columns and the rows. Yeah, we could split up the work here. That'd be like 48 or something like that.
49.32.
Okay, so the chi-square would be 51 minus 49.32 squared divided by 49.32 plus, you do this one and this one, you do them all that way. You probably will never have to do this by hand. That's what I'm going to show you how to do it in this process. So that'd be a chi-square with 4 degrees of freedom. And then you look it up in a table to see if it's significant. In this case, do we want it to be significant or not?
No.
No, because we'd like the groups to be equivalent on marital status. That's what we're hoping for here. But in other studies, you might actually want it to be significant because you're actually looking for some relationship between something and something else. So now in SPSS, the way you do this is 2 different ways to do it. One is very easy. If you actually have for your variables, so remember the way it would be set up in SPSS is you have the actual data file. Would be subject 1, there'd be marital status, married, marital status, and it would be either a 1, a 2, a 3, all the way down for the category of which one they're in. So that would be 1, 2, 3. And there'd be a treatment variable, which would be 1, 2, or 3. Are the 3 treatments. And all you got to do is go to descriptives, cross tabs, chi-square, and it does it for you. It's real easy. But what if you didn't have the whole data set? What if you just had this number? So there's a little trick in SPSS to get it to do it for you this way. That's why I gave you this handout so you can put it away somewhere and remember, because this will come up sometime. It comes up from time to time. So what you do, Lucy, would you mind me to ask Richard how you get these bulbs changed in here? He'll know who doesn't. Bulbs in the
I think it's call IT.
You call IT, they do it?
Yeah.
Well, let's see, maybe somebody did it if we're lucky. But I guess they didn't. Okay, so I created a file to do this. This is a different kind of file, though. I'm going to find it. We'll create it from scratch anyway, and just do it. Okay. So what we're going to do is create a file. Put it in just a very simple file with the numbers that we have here. Since you can't recreate all those 1, 2, 3s, if you don't have them, it's impossible to do it. So rather than doing it by hand, which is a bit of a pain, you can do it by just putting a variable in for the marital treatment. And And then you put a new variable in that's called frequency. You go to data, weight cases. It's a new command we have to use.
What? What did that say?
Data weight cases. It's right on your sheet. And just tell it to the weight the cases by frequency. It's a trick you can use in other settings as well. Then if we go back to the data window, you can see what I did is I put in the data. I actually show you the data here somewhere. Yeah, go to the very back page. You can see I just put in 1 for Mary, 1, 1, 2, 2, 3, 3, and I had already labeled those. Oops, sorry. I had already labeled those previously as married, single, divorced. I put in treatment as 1, 2, 3, 1, 2, 3. But then I go to frequencies basically by those cells we have. You got to make sure you line them up right. 51, 24, 25, 45, 20, 30, 49, 21, 29. Whoops, I didn't put enough things in here. Oh, 3 of these, sorry. Okay, then you go to Analyze, Descriptives, Crosstabs. You put in, you want to kind of decide what you want to be your row or column. Generally speaking, you put in what you think is the outcome measure, which is the treatment as a row. That's what I did. And marital as a column. It doesn't really matter. You got to tell it what statistic you want, Chi-square. Okay. Nice output with all the stuff it does. Okay. Something wrong?
Did you label those variables?
Oh, yeah, maybe not. Treatment by marital. I did. Make sure we get that. Marital treatment frequency.
But did you do it on the other view? Like when you entered the variable names?
Yeah, I didn't label
The
it.
values.
It shouldn't matter. Yeah. Oh, yeah, that shouldn't matter. Maybe I need to, though. You're right. Let's do it. 1 is Mary. 2, maybe 2 need to do it. 2 is single. 3 is divorce. This one is treatment 1, 2 is treatment 2. Go back and make sure I put that weight cases. Oh, that's what I did wrong. It needs to have frequency as the weight case, but I just clicked the wrong element. I didn't think it really had a label, but it's okay. Now it should. Mistakes, I think we got it, yep. Percentage cases, varies, oh yeah, that's right. Oh, and if I put in percentages, that's right, so I just didn't put in percentages, sorry. Analyze, I put it on here though, cross tabs, under cells, you should put third, percentages row, right. Right. You should, it gives you a much better output when you do that, that's right. Now you got what you've got in front of you. And you can see with 4 degrees of freedom, chi-square is 1.142, not significant at all. So you would assure group equivalence here. Okay, just a small little thing, but it's not so easy to learn this without getting the guides to do it.
Is that the only thing that we're looking at for these?
Yeah, so it would be like so for instance, in the study we just did, they give you a table here, because they had 3 groups, workshop only, tape-based, or teleconference supervision. So for gender, for instance, they've got a chi-square of 0.53 with 2 degrees of freedom. For race, they've got Hispanic, African American, Caucasian, other, chi-square of 2 degrees of freedom, 0.91, p less p with 0.64. So they're just assuring group equivalence among those 3 groups. That's what you're going to see very commonly for those. Now, if it's a continuous measure, like age, then you get a t-test or an f-test, right? If there's 3 of them, there'll be an f. If there's 2, you get a t. So the 3 ages were very equivalent. The f was 2 and 52 degrees of freedom, 0.83, p equal 0.52. So you're almost always going to have to do that if you have any kind of an IV.
I said percentages row, but on here it actually says column. It says column under percentages. So are we supposed to do column?
No. I'm just saying. Just decide which one you want the percentages to be in, and and you don't have to do that and still get the chi-square.
Okay.
Just to give you the percentages.
So we would do this under what circumstances?
If you have an IV and you're going to look at group equivalence among your groups before you know, to see did the groups start off equivalently or are they equivalent, then you would use this to make sure the groups are equivalent on category measures.
Okay.
That's the only place to do it.
Okay.
Okay, one other little quick sort of side trick we haven't talked about. Let's say you had a study, this does happen quite often, where you had 11 DVs. Not DV 11. And you're doing, let's just make it simple and just pretend like you're comparing one group compared to the other on those 11 DVs. Group 1 and group 2. And it turns out that when you look at the ANOVAs for each one of those DVs, or t-tests or ANOVAs, that most of them are not quite significant. So 0.08, 0.10, 0.09, 0.05, 0.06, all the way down. But let's say the means, so this is the mean for G1, the mean for G2, are 10, 11, 9, 12, whatever they might be. But in 10 out of the 11 cases, group 2 is higher than group 1. Right? So do you conclude, because you don't have much significance, that the groups aren't different? Or you could say, well, what's the chances of 10 out of 11 of them being in one direction? Right? What's the probability? It's the same probability as flipping a coin 11 times and getting 10 heads. Right? If there's really no difference between the groups, we should have as many group 1 is bigger than group 2, group 2 is bigger than group 1. Should be on the average 50-50, sometimes it'll be 60-40, occasionally it'll be 70-30, rarely would be 90-10. So there is a test for that you can do, which is a sort of a fallback position in these kinds of studies. It's called a binomial test. And you can do it by going online and finding a binomial calculator that'll tell you exactly what we found here. There's a whole bunch of them, actually. So all you gotta do is go online. And Google. There's my Google. Google on there somewhere. Probably that's my favorite stuff. Binomial calculator. This one? No, actually I like the other one better. Sorry. Stat Trek is a good one. So you say the number of trial, the probability of a trial, because this will do it for less than a 50-50 as well. But in our case, we'd always put 0.5 in for that one. So we're talking about what's the probability of a 50-50 split, and then how many trials. In this case, we're saying 11. And we had 10 successes or failures. You can do it either way. And then you calculate. And it gives you the probability. So the chance of getting 10 out of 11 is 0.005. Very rare that by chance alone you'd get 10 heads out of 11 tosses. If it was 9, still significant, 0.026. All right. If we go to 8, however, .08. All right. So we've had a number of instances where we've had results in multiple DVs where one group was bigger in almost all of them, but we didn't get a lot of significance in the individual ANOVAs or t-tests. And so a fallback position is to say, well, it's probably a very small effect if you're not getting significance in each one of them, but overall, it looks like something must be going on because almost every case, group 1 was bigger than group 2. And of course, the more trials you have, the more DVs you have, the better chance you have of that happening. You get 20 out of 21, it's an infinitesimal probability, right? So it's a good thing to know that any situation you have where you're trying to test for 50-50 probability, you can use this binomial test. You don't even have to look it up on the table anymore. You can use this cute little calculator. And don't buy silver bullion, though. All right. So now we're really ready to move on to the more substantial stuff.
So Dr. Gevirtz, would you report those results that you get from the binomial test in your results section?
You just say exactly what we just said, that despite the fact that we didn't have significance, blah, 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 a binomial test was run on all of the 11 dBs, and since 10 of them were in the predicted direction, we assume it's unlikely due to chance that that has occurred. You've got to be a little careful because the fact that nothing else is significant probably means that there's small effect sizes. But depending on what you're doing, it could be important. All right, so the good news is that logistic looks a lot like multiple regression. A lot of the kind of language is the same. The bad news is it's based on a completely different mathematical model. And the second bad news is it involves logarithms. Let me just do a little quick review of what logarithms are. So the easy way to think about it is we'll do log to the base 10 to start with, and then we'll do some other ones, okay? So if you take 10 and you take 10 squared, right, so that's 10, that equals 100. Then the log of 10 squared, the log of 100 is 2 then, right? It's this number is the log. If you take 10 to the third, which is 1,000, that means the logarithm is 3. So the logarithm is the exponent the number needs to be raised to give this kind of a number. So if you are going backwards, you say log of something would be going backwards to the exponent that way. So you can see that the reason we use logarithms for transformations is because it takes 1,000 and puts it down to takes a number like 1,000 and puts it down to a 3. 100 is only down to a 2. 10 is down to a 1, right? So it takes big numbers and pulls them down a lot more than small numbers. It's a scale that expands. Another kind of logarithm is a natural log, which is a constant number, 2.718, which just turns out in nature as an important number, but it's just substituted in for 10. How much does that number have to be raised to give you certain numbers? It's a lot harder to do the math on it because it's a long fraction number. But it's no different conceptually. So if you say you're taking a natural log of something, you're just doing it by a different base. Instead of 10, you're doing it this number that's been determined to be important in mathematics, 2.718, on and on. So we're going to be doing natural logs with logistic. It turns out to work better. But there's nothing it's not as mysterious as it sounds. It's just basically something that worked out to give us a transformation that works very well. And you'll see how it works in a second. So there's major references in this. The two big shots in this one are called Hosmer and Lemschau, who wrote this book back in the 80s, and now the second edition is out. Everybody refers to them as the gurus for logistic regression. There's a newer book out by Menard that's also very good. So if you need a reference to your logistic, you put one of those two down and everybody recognizes those. So it turns out that in modern research, there's a lot of dichotomous outcome data, especially in medicine, but now we're seeing it a lot in psychology too, where in regression type situations, instead of predicting on a continuous measure, we end up predicting yes, no, survive, doesn't survive, passes, doesn't pass, passes their comps, doesn't pass their comps, gets the PhD in time, doesn't get the PhD in time, has a relapse, doesn't have a relapse. So a lot of those measures that are around that are important for us to look at. And so it turns out that there is a really good regression type technique to do it. And there's actually two. We're going to talk about the other one later. The other one is called discriminant analysis. But discriminant analysis has very restrictive assumptions. So we're going to more emphasize logistic regression. And the reason that is, it has very few assumptions, as you'll see in a minute. And it can use as predictors both dichotomous or category measures as predictors as well as continuous measures. In discriminant, it's difficult to meet the assumptions if you don't have continuous predictors. We'll talk about that one later. It's also free of most assumptions that we've had through the year, parametric assumptions. It uses a different concept, though, rather than an R-squared or a beta weight, something called an odds ratio, which we're going to discuss in detail. But it's a really important concept. You see it more and more. The health students especially, it's in all the medical journals all the time. So we really have to get familiar with what people mean by odds ratios. We even actually saw it a little bit, well, in the biofeedback ones. But. So what logistic does is it kind of combines two different technologies. Kind of the thing we saw in Chi-square, crosstabs, classification contingencies between categories, and least squares multiple regression, where the computer can do a million kinds of iterations on the data and get the best fit line. Remember, for multiple regression, we have lots of assumptions, measurement, specification issues, homoscedasticity, normality of the errors, no autocorrelations, no correlations between errors and the IPs, absence of perfect multiple linearity. Those are all things we got to worry about in multiple regression. For logistic, it's much easier. We still can't have too much multiple linearity among the predictors. It can't be too correlated. And we have to specify the right variables in all the regressions. And autocorrelation is still an issue for logistic as well as it is for. So remember, autocorrelation is when observation 1 is correlated with 2, 2 is observed with 3, 3 with 4. That we saw like would be in econometrics, if you were doing correlations among quarters of GDP or something, you wouldn't expect quarter 1 to be independent of quarter 2. They all go in trends. So for psychologists, this becomes an issue if you're doing diary data or longitudinal data on subjects where they're filling out something every day. Remember the example I gave was we did a study on daily stress measures and daily cortisol measures. So if you kind of look at what happens is both stress and cortisol kind of trend up and trend down and trend up and trend down. There's somewhat variability between them. And then in our study we had 2 or 3 instances where some interpersonal stress came in. Like the one I remember best is she writes in her diary, my sister's boyfriend moved in with us because he got evicted. And he's using up, this was the days when phone calls actually costed something. And he's using up all our long distance bill, and everything went up, cortisol. So they're correlated over a couple of days. So autocorrelation is an issue we have to still deal with, but usually it's not. If you thought about a simple situation where you had a dichotomous outcome, survive, don't survive, and a continuous predictor, if you tried to fit a straight line to that, you would have a tough time, right? You're going to get all the continuous measures changing, and then all of a sudden it goes from yes to no, no to yes, right? Because the outcome is either a 0 or a 1. So it's pretty hard to see any kind of linear fit for that. You can't make that linear, so that you can't use linear regression. If you try to use linear regression on data with dichotomous outcomes, you get messed up data. You don't really get a good fit for that. So it turns out that you can do this with if you try to do this with typical linear regression, you can see how badly that regression line fits that data. Right? That's not exactly what we want to have. That would be our typical one. With a typical one, A is the y-intercept, B is the weight of the first variable, B2 is the second variable, and so on. Right? Our typical regression equation. So it turns out that there's a mathematical solution to this that ends up being logistic regression. If we log transform the outcome to make it into a natural log, it turns out that that gives us something like an odds, something like a probability of odds. And that then turns this into kind of a linear regression that we can deal with. So ln is a natural log, odds of the likelihood, so there's a difference between probability and odds. Odds of the likelihood of event of occurring versus not occurring for a given value of a predictor variable. Probability is different than odds. The probability of occurring versus not occurring, P over 1 minus P is what the odds, which P is the probability of event occurring, it's 0.5 chance of occurring, over not occurring, 0.5, then it would be a 1, right? So to do this, we do 2 steps. Probabilities of likelihood of event occurring, the number between 0 and 1. Right? Probabilities are always between 0 and 1. Odds are probability belonging to one or another dichotomous outcomes, and it could be a number between 0 and infinity. You can have odds of 50 to 1, 100 to 1, 3,000 to 1, right? You can't have probabilities of 3,000 to 1, you can only have odds of those. And if you have a more complicated situation, you have something called an odds ratio, which is comparing the likelihood of an event between 2 groups. So an odds ratio would be the event of occurring versus not occurring of an event between 2 groups. So like if you're a member of if you're a member of this group, then you're much more likely to have this occur than not occur. We'll see how that works. So odds ratios are what we get from the output. That's the main output we get from logistic. We don't really care much about regression weights. We do a little bit of a version of an R squared, but it's not really very accurate. Odds ratios are really what we want. So in an odds ratio, if you get a 1, that means the event was equally likely. Right? That means it could happen equally likely for one or the other. Less than 1 means it's less likely. That a status of like going from married to not married would make you less likely. And more than 1 makes you more likely. So what we're going to do is change everything into numbers that go above 1, because odds ratios below 1 are very hard to interpret language-wise. You say there's a 0.92 for a 1 unit change in variable A, there's a 0.92 chance that it'll be survive or not survive. Most people don't know what a 0.92 means in an odds. But if we say 1.5, that means you're 1.5 times more likely to survive. So we're going to always move them to above 1. We're going to change the signs around so they always become above 1. That way we don't have to worry about interpreting odds ratios below 1. So the way it does this, the way the computer does this is similar to regression, but it's predicting this natural log of odds. And so we get a given number, which we're just calling arbitrarily G predicted, which is the natural log of the odds. That number turns out to give us a good regression equation that we're used to, the y-intercept and regression weights. The trouble is this equation now comes in an exponent, as an exponent of an equation, not like it is normally. So you don't have to worry about really doing this because the computer does it, but it's a good idea if you understand how it works. It turns out the reason we have logistic is because it's too hard to do by hand. The computer needs to do 1,000,000 iterations to find the maximum likelihood fit. So it takes all of these numbers and puts them into an equation, figures out the optimal equation that it can find to form these A's and B's. And that's called maximum likelihood estimation, MLE. But getting this G number is not very useful by itself. So what we do is we take the anti-log of that. The computer does this for us, and that's what will be our odds ratios. The actual equation would be the natural, E is the symbol for the natural log, 2.718, or some number like that, to this particular exponent, which is this equation, over 1 minus that one. And that gives us actually, for each person, a predicted probability. 0.5 is the cutoff, so anything above 0.5, we'd say that person's predicted to be in group 1. Below 0.5, we say they're predicted to be in group 0. So if you survive, not survive, pass, not pass, relapse, don't relapse, whatever those categories are in the outcome. And the computer will actually give us a predicted probability for each person between 0 and 1, as well as an odds ratio for the overall variable.
Is it safe to say then with the way you're defining probability and odds, that probability is almost like a percentage?
Yeah, kind of, like we've always talked about, like 0.05 is a probability, right? It's sort of 5% chance. Yeah.
Where odds is like almost like a ratio.
Odds is like what you get at the horse races, right? This horse is a 3-to-1, or in NCAA tournament. So Wichita State was a 350-to-1 chance to make it to the Final Four, something like that. It means that $1 will get you 350. Those are very different meanings of probabilities. Now they probably have probability too, which would be a very small number, right? 0.000 something. Yeah. Sorry, that's so let's take a real simple example and work through the math on it before we actually see how the computer does it. Let's say we were just going to do a simple study where we wanted to see whether males or females are more likely to seek therapy. And we have a big sample. And you have a total of 300 males and 500 females. And we can see that for the males that 200 sought therapy and 100 sought no therapy. And for the females, 250 sought therapy and 250 didn't seek therapy. It probably wouldn't really work that way, but it's okay. So the probability for the sample of 250 sought therapy would be, versus not, is a 50-50, right? If you've got 250 and 250, then you've got a 50-50 chance among females of seeking therapy. For the males, I think I got them backwards. I think I meant to be 50. We want males not to seek therapy, right? The guys don't like therapy. So it would be 50 over 150, or a 0.33 chance. If there were 150 total males, I think I put the wrong number. Then we'd have a 0.33 chance for the males and a 0.5 for the females. But I messed up a little bit, so don't get confused. Yeah, I put the wrong numbers here. So this should have been 50 here. Make that a 50. I did that in a wrong version.
The females is correct.
Yeah, the females is correct. I have the wrong slideshow, I think.
That's 500.
Yeah, there are 500. There's 500 females, I think, and 150 males. That's what it's supposed to be.
So that part is wrong.
Yeah, so forget about it. This one's wrong. Yeah, that's wrong too. So make that 150 and make that 500. I did correct this on the slide, but I didn't pick the right slideshow. Everybody with me? Okay. So now with those numbers, we get a 50-50 chance for females and a 33% chance for males seeking therapy. Right? So thus female is twice as likely to seek therapy as not seek therapy. Right? If we do that, I think that's what
I'm confused. Where did you get those 200 and 100?
Yeah, I think I got the wrong numbers here too. It's 150, 200. I think this was also supposed to be for samples 250 sought therapy, 250 did not. That's right. For females,
250 over
250 over 500 it should. We had that. We had that for the 0.5.
Just that one.
This one is funny. For females, it should be 250. The odds are seeking therapy versus not seeking therapy. So it would be 250 over 5, or 500 over 250, right? That should give us a 2. Should be the other way. So
For the males, do you have them?
So I should have the males not seeking therapy. Oh, sorry. That one should have been 50. That's 150. That's what it is. 50, 150. 50, 150 here. And this should be seeking therapy 250. Or not seeking therapy
So it'll total out as 250 in both columns. I think it's 50 for the males for therapy, 200 for the females for therapy.
Yeah.
150 for the males for no therapy,
Yeah.
and 100 for the females for no therapy.
Okay. Got that?
I was just playing with it on here.
No, you're absolutely right. So therapy, no therapy, male, female. This should have been 50, 150. This should have been 200, 200, 100. Yeah, that's good. Remind me to put the break to fix that. Okay.
Is
Now
it
it-
supposed to be 150, 50, or does it matter?
No therapy. No, that's right. We want the females to be seeking therapy twice as much as not.
And then you wind up with the
Male,
next
no therapy, it should be, the male should be,
Oh,
no, that's right.
That's right. Then the next probability for the sample is correct on the next.
That's right. This is what I wanted. This is what I wanted. So now, moving right along.
So
We've
this,
got-
all these numbers are correct.
These numbers were correct, yeah. So a third of the males sought therapy, twice as many females sought therapy as not. So you'd say males are less likely, females are twice as likely to seek therapy as not seek therapy. We don't compare them to the males. The odds ratio, if we compare those two to one another, and now we put the 2 over the 0.33, this is the important part, and we get a 6 times, females were 6 times more likely to seek therapy than males. That's what we really want out of this. A change in status, gender, makes you six times more likely to seek therapy.
So because you said that it's easier for people to understand with numbers greater than 1, you always put the larger number over the smaller
Yeah,
number
or
for the
just,
smaller
yeah, so
number.
if you get a negative number for it, then you can just switch switch male to female, or switch likely to unlikely, right? If you just change the word unlikely, then you can make it above 1. I'll show you how to do that later.
Okay.
It's just much easier to do. With me now? I'm sorry about that. So if we do the calculation, so we get the computer to do the calculations for us in the same one, just to get the exact same thing. Here's how the computer would handle that same problem. It would go ahead and try to find an equation. Like this looks like a regression equation. Minus 1.099 is kind of a y-intercept number. Plus 1.792 is the regression weight, the logistic regression weight for gender. So for a female, for instance, who would be coded 1, their probability would be 0.693. We just plug in 1 into that equation here and solve that equation, we get a 0.693. With me? Okay, if we use the anti-log formula and put that equation into that little formula there, we get 2.718 to the 0.693 over 1 plus 2, which gives us a probability of 0.667 for that particular person. A female would have a 0.667 probability of seeking therapy, 0.5, so we would predict that she would seek therapy. If we did a male, we would get the same equation would hold, but we put a 0 in there because males are coded 0. And then for that person, we plug it in the formula, we get a 0.250, so that would make a male would be not likely to seek therapy, so below 0.5. As you said here.
So they're 25% not likely to see therapy?
No, this is not a percentage. This is actually a cutoff. Well, the probability of them seeking therapy, I guess if you want to use a percentage, you could say a 25% chance they would seek therapy.
But they would.
They would, yeah, compared to,
The whole sample.
but we really don't do it that way. We just use that as a kind of a general predictive value for that person.
Appraisal value sort of thing.
We'll do those later, but this just gives you a number like a predicted value in regression for that person. In logistic, the predicted value is always going to be between 0 and 1 for each person. And when we have more complex ones, we'll have lots of numbers in between. So you could say, okay, well, this person, say for instance, somebody that was predicted, the predicted value was 0.48, we're not so sure about that person, right? They could be, they're almost above 0.5, they're just a little below 0.5, that's not a very good prediction. Someone's a 0.1, we've got a really strong prediction that they will not seek therapy.
For the male, when we plugged in 0, is that just because?
We coded male 0, yeah, we just coded male 0. And you need to know how you coded them. If you coded them 1, 2, then you'd plug in a 1. It would work the same exact way.
And the difference between the anti-log and
So then we basically go back to that other equation and take the anti-log out of that to get these probabilities. These numbers by themselves are not too useful, so we end up getting a better number out of them when we do it this way. Otherwise, we're not getting the real mathematics behind that prediction. Because the prediction is to a G number, but the G number doesn't mean too much by itself. If we turn that into an anti-log, that number actually becomes a probability. It's just the way the math works of it. And then we can get that same odds ratio if, I think I might have a typo on your slide there, on the ones I gave you. But the 2.718, which is the natural log, to the power 1.792, which is this regression weight, also gives us the odds ratio of 6.0 that we got the other way. So that's the way it kind of gets into that particular way on more complicated examples. So now the key is what happens if we add another predictor to the equation. We can't do it anymore the way we first did it with just those nice little ratios anymore. Now we get a much more complicated thing, but the computer handles this beautifully because it can run a million times through and get the best equation. So now we're adding depression to this equation, saying, okay, we have your pre-depression score and your gender. We're going to use those two to predict how likely you are to seek therapy. It makes some sense, right? So we know that gender plays a role in seeking therapy, and probably depression does. But now, how about the two of them together? Can we kind of figure that out, just like we would in regression? So the computer figures out the regression equation, and that's what it is. And those numbers are determined by lots of iterations. So, for instance, if we just plugged in arbitrarily a Beck score, say, of 40 for a male, so we give them a 0 here and a 40 for depression, they come up with a minus 0.311. We go through that little anti-log equation, we get a 0.042. So a male with a depression score of 40 would be quite unlikely to seek therapy. So I'm using an arbitrary depression scale, like 1 to 100, so it's not a Beck. For a female with a depression score of 75, so that'd be a depressed female, which is probably all of you in the room after this lecture, we just plug in a 1 and a 75 into the equation. We get this number, which we take the anti-log of, and we get 0.973. So a depressed female will be very likely to seek therapy. Right. We'll sign you up right after class. And we can get an odds ratio out of this. Now this is called an adjusted odds ratio because it's the odds ratio for each one of those separately. For gender, it's the natural log raised to its exponent, and it's 8.404. So that's the odds of seeking therapy versus not seeking therapy for females versus males seeking therapy, holding constant depression, just like in regression. Yeah, so the 8.404 is the likelihood of a female seeking depression, seeking therapy, seeking therapy, holding constant their depressive score, as if we had everybody with the same depression score. Or we could do it the other way, for the depressive score, and say, for depression score, E is 1.14, so a 1 unit increase in the depressive score increases the odds of seeking therapy by 1.14 to 1, or about 14%. So you always take the number above 1 minus 1 for the percentage. So for females, for a depression score of that particular one of 75, sorry, for a 1 unit increase in any depression score for females, we can say for each unit more, they'd be about 14% more likely to seek therapy holding constant gender. Not just for females, for anybody. Get that one? That's the equivalent to our beta weights. But the beta weights don't work, you have to do it with odds ratios.
So again, that's a 1 unit increase for depressive score in females.
No, for anybody. A 1 unit increase in depressive score increases the odds of seeking therapy by 1.4 to 1, 1.14 to 1, which you sometimes think of about 14%, controlling for gender. That'd be for anybody.
Okay.
And if we wanted to say, well, okay, that's a 100-point scale, a 1-point unit doesn't mean too much, maybe a 10-point unit means something, right? You have to multiply that 10 times the exponent to make this a 3.71. So that would mean a 10-point increase in the depression scale would make one almost 4 times more likely to seek therapy with gender held constant. So a 10-point might be a meaningful change on that scale. You can always adjust that any way you want it.
So the other one is the equivalent of the unstandardized grade?
Yeah, there's no standardized ones here. They're all kind of unstandardized, but they're on odds ratios, not on, we can't say a 1 unit increase makes another increase. It's always in terms of an odds ratio.
For that first odds ratio, you would say the odds of a female seeking therapy holding constant for depression score, but is it
Also person.
like how do you know that that's the females and not also males?
Up here?
Yeah.
Oh, I just arbitrarily chose a female with a score of 75, just as an example. Could be
Oh,
anybody.
no, not that part, just below that.
This one.
Yeah.
Okay, because once we get to the odds ratio is not coming from here.
Yeah.
The odds ratio is coming from here, from the exponents, right? So that's true for everybody. That just means
So it's the odds for males or females seeking therapy.
you're going to get an odds ratio for each variable, one for gender and one for depression.
Right.
So for gender, we're saying, okay, it's like a 1 unit change, but it's going from male to female is the 1 unit change. It increases your odds of seeking therapy by 8.404 to 1.
So me being a female increases my odds by 8.4 versus you because I'm a female.
Right. And that's holding constant depression score. Right.
So if your depression scores were the same.
Yeah, we have the same depression score. I'd be 8.404.
Right.
More times likely.
Exactly.
To seek therapy than
Exactly.
you're right.
Do you need the same depression score since it's holding constant?
Do you need?
Yeah.
That's what it tells you. When they are.
Okay, so holding constant means
It's always holding constant whatever else in the equation, just like in regression.
Okay, yeah.
So we'll look at some real examples of how SPSS does it. The two we're going to use are one study we did ourselves on finishing your dissertation on time, yes or no. And the predictors of that were, we ran it over several years, were did you think, we asked them to, how much was the topic of internal interest to you? How expert was your chair in the topic? How available was the chair to you in office hours? And how many hours a week did you work during this time, on average? Okay. And then the other study is one that the health students have seen. It's a study we did, a bigger study with whiplash patients where we tried to see whether seeing a particular video changed their outcomes of using narcotic medication. I'll go through that in a second.
So hours a week of work, was that working at a job or working
Yeah,
at
working
a
at a
dissertation?
job. No, that was working. How many hours a week did you work in your dissertation?
Okay.
We hoped that they were telling us the truth, but we know they weren't. So let me show you the results. I think you've got them in front of you, but I'll put them up here. Let me show you how to do it. It's actually really easy to do logistics in SPSS. first one is put it on my thumb drive, that's not good. Let's see. That file is called On Time. If I can find it. You have to run those directly. You can look at the output anyway, and I'll show you on the other one how to do it. So look at your, don't worry so much how to do it, it's actually very easy to do it, so. So I just gave you actually a couple pages here for logistic. So all I did is I went in and I put finishing on time as a 1, not on time as a 0. I put in the predictors being those variables we just saw. And you can see them on the second page. Now you get some output here that's a little bit new, so let's go through that output. The first thing is it gives you a kind of a chi-square. And what this chi-square is doing is it's creating, on page 2, it's creating a model and taking the difference between the default model, the model without any predictors versus the model with predictors. And the amount that this number goes up, this negative log likelihood. So what happens out of the equation is you get, see the negative 2 log likelihood? Sort of an arbitrary number. It starts with a null data set without any predictors. The amount that you're able to lower that log likelihood is the amount that your prediction is working. So it's kind of like our delta R squared, but it doesn't, you don't get one of those. So here you can see that the model with all the variables in did give us a very significant chi-square. That means a big difference between the two, the null model and the actual prediction model, which is what we want.
So you do want chi-square.
You want this one to be significant. This is going to be confusing because the next one we don't want to be significant. So this is one that looks at how much we added to the model. So it would be like a delta R squared in regression, where we saw how much R squared was added by the variables. And we want that to be significant for sure.
So it's like this one, this one.
The one on the top, the 24.351. Now how they get that is it's a little tricky. It turns out the numbers tend to be negative numbers, and so they decided to do a negative log, to multiply it times -2 to make them positive numbers, just arbitrarily.
And you want that to be significant.
So you want that to be significant. Now sometimes we're going to put in variables in steps or in blocks, right? And then you get the difference between one step and the next step. Again, you want those to be significant. Right now we put them all in at once.
Because you want your predictors to be adding greater than chance.
Exactly. So we're predicting variance accounted for, just like in regression. It's just a little confusing because that number, that negative log likelihood, comes from all this logarithmic stuff.
How would we annotate that -2 log likelihood?
You would just say the -2, the -2 LL is such and such, or mostly people just say the chi-square was significant.
Okay, so there wouldn't be like a question that says, blah, 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 blah. How what would we
Well, you would never, those numbers don't mean anything by themselves.
Okay.
They have to be put into a chi-square to tell you anything.
Okay.
Yeah, so.
Is the difference between our null model and
and the prediction model with all the variables. In this case, with all the variables. It also gives you two attempts at an R squared. So people don't quite agree on this one. So there's two different equations that are used to try and turn that negative 2 log likelihood into a number that we all understand, like an R squared. Except that you can see they're not so close to each other. Most people use the Nagel-Kirke one, the second one. But not everybody agrees with that. So in some ways, it's probably better not to do the R squared unless you just feel like the reader needs to know how much variance is accounted for. So it's either 39% or 51%, depending on who you believe. So you have kind of a, and it's not exactly right because it's not variance accounted for. It's really better to look at the prediction.
So stay away from it.
You could try to stay away from it, but you need to know that these are R squared approximations. So there's just two versions of them. I think the book tells you which one it likes. I forgot which one. I think he likes the Nagel version. Now the next one is a little more confusing because this chi-square we do not want to be significant. The Hosmer and Lemschau test, named after our famous founders of logistics. What they do here is come up with an attempt to look at homoscedasticity. And what they do is based on those predicted scores that we got before, like between 0 and 1, 0.37, 0.75, whatever they were, it divides the sample into deciles as best it can, into groups of 10, from lowest to highest. And it does that for those who finished, didn't finish on time, that's the zeros, and those who did finish on time, those are the ones. And then it does a chi-square in those, basically predicting expected, just like I did in the board, first thing, expected versus observed, squared, added up. And what you want is a good fit between what's expected and what's observed. The reason this is in there is because if there were one of those cells that was way out of line with what's expected, it would tell you that maybe something's wrong with your model. It's the only way we have of looking at something like homoscedasticity. So it's not great, but it's the only thing we have in logistics. The important thing is you want this not to be significant. Okay, then it gives you an important thing, a classification table. And what it does is it takes every single person, calculates their predicted value from 0 to 1. If they're below 0.5, we say we don't think they'll finish on time. If they're above 0.5, we think they will finish on time. Right? And we do that for those who really did finish on time and those who really didn't finish on time, because we have the records now. And so you can see that we got 20 people we didn't think would finish on time, they didn't. 17 people we thought would finish on time who did. 6 people we predicted that they wouldn't finish on, they would finish on time, but they didn't. And 7 people we predicted they would and they didn't. We predicted they wouldn't, we predicted they wouldn't and they did. They surprised us. You see those?
So zeros are...
0 means
yes.
didn't finish on time, one we did. And so on the predicted is 0 means we predicted they wouldn't, we predicted they would.
Okay, so 17 people, we predicted yes, they did.
Exactly. And 20, so those are true positives, right? True positives. No, those 17 people are the true positives.
Where we predicted and they did.
You can write it in there because we're going to use these numbers, we're going to use these abbreviations. 17 is TPs, true positives. See the 17? Up on the top of page 3.
Dr. Gevirtz, you said that this is actual data.
Yeah.
You had 20 people that didn't finish their dissertations.
Well, I mean, it's not out of everybody. This is the ones we got from the sample.
Over many years ago?
This is on time. This doesn't mean they didn't finish it. They just didn't finish on time. So we give people in the PhD program, we give them 5 years. And then if they were more than a little bit beyond 5 years, they didn't finish on time. If they finished within the 5 years, they did. That's how we did that.
So under the 1.00 is usually the positives?
So see the 17 there, those are the true positives. 20 are the true negatives, right? Okay, how about the 6? Are they false positives or false negatives?
False positives.
Because,
False negative.
False negative.
what's your logic? Why do you think so?
In Dr. Mona's class, it's
Because we.
flipped.
Yeah, you can flip them. I actually like it the other way
We
too.
falsely predicted that they would not finish on time.
So we falsely predicted they would not finish on time. So those, we'll flip them around the other way. I don't know why.
6 is false negative?
False.
So the 6 are false
Positive.
positives, the 7 are false negatives.
No, they're false negatives.
I'm sorry, the 6 are false negatives, the 7 are false positives. Yes, the way Dr. Mano does it, and I like the way she does it too. So.
7 are false
Wait,
positives.
one of them did finish?
So the 20 and the 6 are the
Why did they
negatives.
false positives?
Not-
And the 17 are
Because we didn't predict they
So
would be on time.
we predicted they would finish in time, and they didn't.
Is it false
But
positive?
that's a false positive.
For the 7.
For the 6,
For the
yeah.
6.
6 is a false positive, 7 is a false negative.
Okay.
Got it? 6 is a false positive, 7 is a false negative.
Got it.
Yeah,
Yeah.
usually we flip them. Well, and I have another handout where I did flip them actually.
So 7 is what?
And they did it.
7 is a false negative.
You're missing me.
Okay, so now-
So just say it to yourself what we thought and what really happened. That's what the important part, right?
Because usually when I document, it's like one.
I know. I have another
So
handout.
the column is positive, the other column is negative.
Right, you can do it. A lot of people do it both ways. You just have to make sure you know how it works.
Is the other way you have are the predicted and the
No. I think everybody is predicted, and we'll see.
flip the other.
Yeah, just flip the other one, unfortunately.
Predicting
6 was the false positive.
they were false positive.
Yeah.
So
That's
it's
why we use this like, no, this is false positive. Because you predicted that they will.
Yeah, so the usual way we do it is true positives, true negatives, false positives, false negatives. So that's how this one is. That's right. If she does it differently, this is the way most people do it.
So this 0, 0, and 1 professor tells us anything about the negative and positive?
Yeah, so you could, I just didn't label it as a finish on time or not finish on time. So you just need to know how you label them.
Oh.
So 1, just write in there, 1 means finish on time, 0 means didn't. And then you can look at those. Okay, so we got the 74% is the hit rate. It's called the hit rate. We were 74% correct. That's 20 plus 17 divided by the total. It's 54 as a total. See the 74 at the top of page 3?
it's what?
It's a hit rate.
So it's all correct.
Those are the ones we got right.
Those are all the above.
Yeah, and 26% we got wrong.
No.
Right?
They're not horrible.
They're not horrible. Okay, so now what was this is the important take. 20 plus 17 divided by the total, which is I think 54, right? So 20, 37 and 13. 26, 26 and 24. No, it's more. It's not. I haven't got the total right. How much is the total? 26 and 24 is 40, right? 26 and 24, 50. So it's 20 plus 17 divided by 50. Should give you
Would you be able to
7.
calculate that?
It does it for you. Calculates the hit rates. Just so you know. All right, we okay for the classification table? We'll go back through another one later. All right, now we get the actual important output here. So you get a B weight, but those B weights are kind of not very interpretable because they're logs. And so you can't really do much with them. But they do give you a standard error. So that means that we're doing like Monte Carlo studies with thousands of repetitions for this model. with the data not being true, and what would be the distribution of the B weights, and it turns out to be a skewed distribution, and that's why we use this called walled chi-square for the actual significance level. So that walled is like another kind of a chi-square, and it's divided by, you look it up with its degrees of freedom, and it gives you the significance, but the computer does that for you. Okay, so we can see that among those predictors, really only the chair expertise, remember they're all in together, only the chair expertise really is significant. So that's the only odds ratio we really want to interpret. Only the significant ones are the odds ratio is interpretable. The odds ratio is 2.209. So this is a real take-home message here. For every, the chair expertise is only on a 1 to 7 scale. So for every 1 unit your chair is more expert in the topic you're choosing, you're more than twice as likely to finish on time. If you went from a chair that knows nothing about it to someone who is a super expert, you can go up 7 points on that one. You can multiply those units in the times the log, take the anti-log of that, and it comes up to be, I think I did it here actually, did I?
So it's more important to pick what your chair is interested in than what you and you.
Yeah, well,
It's the opposite of what every professor will ever say.
no, it isn't true. No, most of us would say you need to get a compromise between what you're interested in and what the chair knows something about. It's not necessarily interested. Some of the chairs might be bored to death by what their expertise
So
is
just
in.
their, yeah.
Hopefully not.
For every 1 unit, your chair is more expert in the topic you're choosing.
You're more than twice as likely to finish on time. Then I did it with all the other variables held constant. No, I didn't do the multiplication for you here, but
So the XB column is what tells you how
yes.
much
See, I labeled it odds ratio. For some reason, SPSS wants to, it's the exponent of B, which is technically what an odds ratio is, but I wish they would just put odds ratio for that. Everybody else calls it an odds ratio. So remember that XB is, those are odds ratios.
So those are the ones we look at instead of the significant.
Exactly. That's the most important output we get. The B weights are not like standard weights. They don't tell you much of anything by themselves except they're used for significance. You got to get significance first. Once you're pretty sure that's a real variable, then you can interpret the odds ratio. Now, if you wanted to see how much two units of chair expertise is, you'd have to multiply 2 times 0.793, and then take the anti-log on your calculator to do this. You do need to learn to take the anti-log of natural logs on your calculator, because a negative number, what we're going to do is we're going to just take the positive one and change the language. We have one coming up. It's a negative one. I'll show you that. So figure out on your calculator, ln is the natural log, and you just have to put the shift button first before you push the number, and then it'll give you the. You can try these and try to put 0.793, see if you can get 2.209 on your calculators. Why don't we do that first? 0.793.
Just 0.79.
It should come out 2.209. So you do that with the anti-log of 2.21. 2.21, yeah, exactly. You got to do the shift first, though. That's close.
What
That's
is that, the natural log of 0.7?
2.2, yeah, that's close.
Is it like error or something?
Yeah, well, it's just rounding off. It's just rounding off in your calculator.
Negative 0.23.
No, you didn't do the shift number, that's not right.
Mine doesn't require a shift.
It's 2.209.
Just for the anti-log, you're just doing ln, right?
Yes.
No, you got to do something, whatever your calculator does. Who's got, you got a TI?
Yeah.
How do you do the anti-log?
There's going to be a shift or some other button first, no?
Because you have to press second to get into the log. So you have a log, a 10 to the power, a natural log, and e to the power.
E to the power,
An
yeah.
anti-
Yeah, it might be your symbol, e to the power.
Oh, the exponent.
So you
Okay.
just push that one, right? And then you push
No, that won't work. That's not the anti-log. So let's see what we got, e to the power.
Oh, yes, right here. So
Yeah.
right. Okay, so I do that. And
Yeah.
then 0.793.
2.21.
Okay.
Got it. Everybody got it?
Can't argue with that.
You can do it on your computer too. You can do it in SPSS by just doing a transform. But so let's try one. Let's say 2 points. Multiply 0.793 times 2. Tell me what that number is.
2 times. That's right. 1.586. 586.
Okay, now take the anti-log of that one.
4.884.
884? Correct. Almost fine. So if you go from a chair who has no expertise in the topic to one that's on a scale 2 points higher, you increase your chances of finishing in time by almost 5 to 1.
Wow.
Probably this is because if your chair has expertise, they have some investment in the study, and they know something about it, so that you don't get sort of out on a limb, so it really kind of goes much more quicker. And that's with everything else held constant. So notice that the amount of hours you spend a week doesn't matter. Now it might matter by itself. It might matter by itself. How would we find out by itself how many hours?
If we held on the constant, you mean?
No, if we didn't hold the constant. Just if we wanted to look at hours,
Worked on.
hours worked on, whatever that one's called here. It must be IGS or something. No. Joy. Maybe it's the joy.
Dissertation time?
Oh, disk time, that's what it is, yeah. So if we wanted to just see disk time with the original data, you can't do it from here, but how'd you do it?
Enjoy is the variable.
How did we always do it when we wanted to do variables by themselves, not influenced by anything else?
Normal and constant.
Not holding constant. What did we do when we don't hold constant?
So would you put it into an equation?
No.
One.
It's when you always miss on this same exam time and time again. No. No, you just use a straight correlation by itself, right? If you want to know by itself, you don't put it in an equation, you just do it by itself. So what you would do is either just use a point by serial or just put it into the equation all by itself with nothing else. And it could be that those hours are important, but it may be that they co-vary with chair expertise.
Could also be that most people spend about the same time.
It could be there's no variability in that too, that's right, or at least they told us that.
Well, yeah.
I work 300 hours a week on my dissertation.
And the last part of it is not very interpretable here, but it's like a graph that shows you, we'll see it on a real one, you can see it's more interpretable. Basically it does a graph of who finished on time, who didn't, and who we predicted, and puts it on a scatter kind of, so you can see where your mistakes are. This stuff at the bottom didn't print, yeah, it didn't print, but I'll go get my thumb drive and show you how that works.
I didn't know where it went in that part. To get that question wrong.
All right, so maybe we will stop there, take a break, come back to the SEM, and then next time we'll do another example of logistic completely. I'll have the data on my thumb drive this time, show you how to do it. What's the homework for this time? So that is the one we're going to do in class, actually. So we're going to do it in class, and you can just take it and turn it in. Because I want to work, I couldn't find a really good example that we could all work on. This is a pretty good one. We can kind of form them out. I don't think we're going to do it exactly the same way they do it, though. We'll mess with it a little bit. Right. Okay, so take a break. Let's make it just a 15-minute break.